Parallel circuits, Ep59, the three properties and lightning-fast solves. Crash course instrumentation. Parallel circuits, cold open, hook. Want to solve parallel circuits in under a minute without memorizing formulas? Today you will learn the three core properties of parallel and a simple step-by-step method that turns any problem into easy numbers. By the end, you will be able to spot parallel instantly and calculate currents, equivalent resistance, and power with confidence. The three properties of parallel, clear and visual. Same voltage across every branch. Think of two rails, a top rail and a bottom rail. Anything connected from the top rail to the bottom rail is a parallel branch and sees the full source voltage. Currents add at the source. The source current is the sum of the branch currents. Each branch decides its own current based on its resistance and the shared voltage. Equivalent resistance goes down as you add branches. The combined resistance of a parallel network is less than the smallest single branch. Quick solve method, VIRP in plain words. Step 1. Mark the two common nodes. Everything between those two nodes is in parallel and shares the same voltage as the source. Step 2. For each branch, find its current using Ohm's law in words. Current equals voltage divided by resistance. Step 3. Add all branch currents. That sum is the source current. Step 4. Find the equivalent resistance in words. Divide the source voltage by the total current. Step 5. Optional power check. Branch power equals voltage times branch current. Total power is the sum of branch powers or source voltage times source current. Worked example in narration. Pictory-friendly. Picture a 12-volt source feeding three resistors in parallel, 120 ohms, 60 ohms, and 30 ohms. Branch currents. 12 divided by 120 equals 0.1 amperes. 12 divided by 60 equals 0.2 amperes. 12 divided by 30 equals 0.4 amperes. Total current. Add 0.1, 0.2, and 0.4 to get 0.8 amperes from the source. Equivalent resistance. Source voltage divided by total current equals 12 divided by 0.8, which is 15 ohms. Optional power. Branch powers are 1.2 watts, 2.4 watts, and 4.8 watts. Total power is 8.4 watts, which matches source voltage times source current. Common mistakes and quick fixes. Thinking branch voltage changes. In parallel, each branch always sees the full source voltage across the two common nodes, forgetting that currents add. If your total current is not equal to the sum of branch currents, you missed a branch or misread a value, expecting equivalent resistance to rise. In parallel, adding a branch always lowers the equivalent resistance and raises the source current, assuming currents split evenly when resistances are unequal. The smaller the resistance, the larger that branch's current. Quick contrast with series for memory hooks. Series keeps current the same and voltages add. Equivalent resistance increases by summing values. Parallel keeps voltage the same and currents add. Equivalent resistance decreases as you add branches. History bite. In the 1840s, Gustav Kirchhoff articulated the current sum rule that underpins parallel circuits. The total current entering a node equals the total leaving it. That insight helped engineers build reliable lighting and telegraph networks, where many branches shared the same supply without dragging each other down. Quick recap for retention. Parallel. Same voltage across branches. Currents add. Equivalent resistance drops as you add branches. Solve fast. Find branch currents with Ohm's law in words. Add them for source current. Then divide source voltage by total current for equivalent resistance. Use the series contrast to lock it in. Series equals same current, voltages add. Parallel equals same voltage, currents add. Outro and call to action. You now have a lightning-fast method for solving any parallel network. If this helped, please like and subscribe so you never miss a Crash Course Instrumentation episode. Special thanks to Tony Coupalt and the open source community for making world-class learning materials freely available.